Hi everyone, welcome back to our channel. Today we are going to study about the transformer coupling. Okay, so let us try to consider a transformer primary. This is primary of an transformer consisting of an voltage source which offers a resistance of R1 ohms and which the primary has an inductance of L1 Henry, and the current which flows in the primary, which is nothing but I of t, and the voltage applied is an sinusoidal which is V1 of t, and I have the secondary winding of the transformer with resistance of R2 and it is connected to the load. Okay, let's try to understand. I have been short circuited the secondary, and the resistance at secondary is R2, and to this inductive coil I have a dot at this end and I have an dot at this end, and here the current flows. This is the load which is short circuited. The current flowing to the transformer is like this. Okay, so now we need to find out the transformer coupling. Okay, so now whenever the current flows, the terminal is positive and leaving is negative, entering is positive, leaving is negative, and these are mutually coupled with a mutual inductance of M. So now voltage source is there. So what we are going to write down is we are going to apply Kirchhoff's voltage law at primary of the transformer winding. So now the voltage, it's an AC supply, but there's nothing right wrong writing the polarities. So let's try to write down the polarities, which is nothing but which is V1 is the voltage source. The drop is I1. So I1 into R1 is the drop, and the voltage across the inductor is given by the formula V equal to L di by dt. This I am going to write down as L1 d I1 by dt, and it has this inductor has an mutual inductance. To this coil, the current is flowing like this. So dot is there at leaving, but in this secondary the current is flowing the load and dot is there at leaving. So I can say that both are at leaving. Here the current is at leaving and this also leaving. Automatically you will get the mutual inductance as M into d by dt. What kind of current? This mutual inductance is due to the current in secondary coil, that's why M2. Okay, so this is how to write down. So similarly apply Kirchhoff's voltage law at the secondary of the transformer. So when you come to the secondary, so the current flowing is entering as positive, leaving as negative, and the current is flowing like this, entering as positive, leaving as negative. There's no source here, therefore voltage source is zero. The drop is okay. So the drop is I2 R2, and the drop across the inductor is V equal to L di by dt, and it is offering an inductance of L2, where I can write down it as L2 into d by dt. And what is the current which is flowing in this branch is I2 current, so I'm writing it as I2, and that's all. But it has a mutual inductance. Here you can see here current is leaving the dot, and here also current is also leaving, therefore you have the mutual inductance is M into d, and this mutual inductance is due to first coil, which is nothing but d I1 by dt. This is how to formulate the transformer coupling. So or you can form in one more method also. Let's try to convert directly into the required format. This is one more inductor, and this is forming an closed path with an AC supply, and here this is of R1 resistance, inductance of L1, and then at secondary, so this is the secondary, and you have an resistance and the secondary is short circuited, the inductance is L2 and this resistance is R2, and the current is flowing in this direction. This is positive, negative, and the dots are there at this end and at this end. The importance of dot is it indicates the polarity of induced EMF. What is the polarity of induced EMF in the winding? It indicates the polarity of the induced EMF. And when you see here, so this inductance I'm going to write down in AC format, which is nothing but plus j xl ohms. This also I'm writing it as xl can be written as omega l ohms. Here it is xl1. So here this inductance I'm going to write down it as plus j xl ohms. This is l2 ohms. This I can write down plus j omega L 2 ohms. So the mutual inductance between these two coils is M. This I am going to write down it as is nothing but plus J X mutual ohms. How Xm can be written as is plus J omega L is nothing but M ohms. Now try to write down in our required format. So voltage source applied here is V1. Okay, so V1 is equal to is the voltage source. What is the drop? So drop, a current of how much is flowing? I1 current is flowing. This I can write down it as I1 R1. So the drop here it is. So this is also like a resistor. I'm going to write down I1 into plus J omega L1 ohms plus, okay, you see here the current is leaving and here the current is also leaving, therefore you are going to get plus I1 into plus j, what is the mutual impedance, plus j omega m ohms. Okay, so here when you take I1 as common in all the things, so here this current mutual inductance is due to which coil? Second coil. So you can write down V1 is equal to, taking I1 as common, which is R plus J omega L1 plus I2 into plus J omega M. This is how to write down with respect to that thing, but we transformed it, that's all. And coming to this equation also, it apply the Kirchhoff's voltage law at the secondary of the transformer. Okay, so the current is flowing like this, there's no source, we can write on it as 0, and the drop here we are going to write on it as I2 R2, and the current is flowing in this direction, therefore it is positive and negative. The voltage drop you can write on it as LdA by dt, and this inductor is, the current is I2, and the inductor value we are going to write down. What is the inductance value? This is plus j omega L 2 ohms, and this is mutually coupled, and you can see here current is there at leaving of the dot, and here also at primary also current is there at leaving of the dot. Automatically you are going to get as this, as this is due to the mutual inductance is due to the current I1, and the magnitude of mutual inductance is plus j omega m. So 0 is equal to, take I2 as an common term. If you take I2 as an common term, we are going to get I2 plus j omega L2 plus I1 into j omega m. So when you compare with the standard expression, so as per finding the Z parameter, V1 is equal to Z11 I1 plus Z12 I2 is one equation, and V2 is equal to uh, Z21 I1 plus Z22 I2. So when you compare with the standard expression, the value of Z11 is equal to R1 plus J omega L1, Z12 is equal to plus J omega M, Z21 is equal to plus J omega M. Just to compare with the expression, and Z22 is equal to R2 plus J omega L2. This way of analysis is called as the modeling or the transformer modeling of transformer coupling. So modeling means the analysis of transformer coupling. So this is how to understand the modeling of the transformer. So when you see here, what kind of current inflows in an transformer, what are the possible mutual inductance possible in an transformer. So I'm taking the transformer, this is the primary of the transformer, this is the secondary of the transformer. Here the current I1 is flowing due to the voltage of and here it is short circuited and load is connected. The current flows in this direction as I2, and here the dot is there at leaving, and here also the dot is there at leaving. Therefore in the formula you are going to get plus m. And for the same circuit, this is primary of the transformer and this is nothing but the secondary of the transformer, where primary is excited with AC supply and second is connected to the load. Okay, therefore the current flows in this direction, which is I2. Here the current flows in this direction, which is nothing but I1. Then how to mark? So here it is there at leaving, so here it will have it entering and this will have it entering. So you can see here the dot is available at the entering of currents. This dot is there at entering of current. Therefore we are going to get the mutual inductance as plus m. Here the dot, both the dots are there at leaving of current, therefore you got minus m. So everything all about how the current enters and leaves. So this is how to write down, and the same network I can give you one more analysis. So this is one inductive coil of the primary and this is nothing but the secondary short circuited. Here we had seen this is there at leaving and entering. Now let us see here, the current I1 is flowing. Current, for current I1 dot is there and current is entering. For the current I2 the dot is there at leaving. Okay, so one is there at entering, one is there at leaving. Okay, so for the current direction as shown here with the resistance of R2. So here for the current I1 it is entering, for the current I2 it is entering, therefore I'm going to get minus m. These are the four possible ways you may get the problems. Okay, so this is the primary of the transformer excited with AC supply, and here the current is there at the leaving with a magnitude of I1, and at the secondary of the transformer with short circuited. So the current I2 is flowing, it is short with a load, let us take it this as an R2, and current is flowing in this direction. So here this is there at leaving and here it is there at entering. So here you can see here one is there at entering, one is there at leaving, that's why minus m. Here it at leaving it have current is leaving, we have dot, and current is there at entering, here also we have minus m. So that's how the mutual inductance values are different for different flows of current into the dot. So that's how this plus m minus m we are going to decide. So this is all about the modeling of the transformer. Just write down the Bessel KVL equation, and to reduce this are called as differential equations. These are called as the direct AC analysis. Okay, so this how to write down the transformer modeling in Z parameter model. These are the four possible ways the transformer connection we have plus M and minus M. So both currents are leaving, both the currents are leaving, the current is leaving, the dots are there at leaving of the currents. Here the dots are there at entering of the current, that's why entering or leaving automatically plus m. Here the dot is there at entering and dot is there at leaving, here the dot is there at leaving and entering, automatically you will get minus m. This is how to mark the mutual inductance. Hope you understood the content. If you feel the content is useful, please like the video, share with your friends, and if you're watching for the first time, still if you have any doubts in my explanation, you can comment me, I will answer your comment. And if you're watching the channel for the first time, subscribe the channel with the name kV Tulasi. So hope you understood the concept. Yours obediently wrong. We'll meet in the next video. Thank you for watching.